Thank you all. As I think I've met, I've met many of you running around, so talking with friends, I hope. All right, so this is stuff I did with my friend Alan Brown. I've met Alan years ago on the XML schema working group, and we've been together, and he invited me to take part in this, and I've been an amateur category theorist for many years, and was like, ooh, I can actually use some of this stuff to do something. Sounds like fun. So Alan is in charge of Deixis Digital. He's been working on smart contracts, digital twins, and provably correct software. So what we're trying to do is, how do you model a physical process in a mathematical way? And so the process that I'm going to address is a simple one. It's a recipe for making a lemon meringue pie. And the reason we picked this one is there's a applied category theory group of mathematicians, and this is one that other people have used, and we wanted to sort of firm it up. So this is kind of a wiring diagram. All of the boxes are various steps in the process, and all of the lines are inputs and outputs. Yeah, so what is a digital twin? I mean, on the left, it's basically the notion of a digital twin is a reflection of the physical twin, and they want to talk to each other. So you've got you've got some glue code in between, which I won't be talking about. So I'm basically talking about the digital side of things. At the moment, these are very expensive things to make. You go to IBM and you pay them millions of dollars, and they will create a digital twin of your factory, which, of course, was all actually generated from a CAD system. So you're wondering, why is it that you need to reverse engineer this thing when you started a bunch of digital files in the first place? But what we're looking at is, how do you treat that mathematically? You know, can you look at these things and particularly through the lens of category theory? So that's what I'm going to be talking about. And then we were like, okay, once you can do that, how do you what can you do with that? Can you program with it? Can you write code around that? And so we've chosen to work our implementation in Agda, which is a dependently typed language, and it sort of tries to make the balance between a programming language and a proof assistant. So there are enormous libraries of mathematics with proofs around Agda. And as I mentioned at the bottom, you have other languages of the same sort, Idris, and particularly Lean. And it seems, I mean, I don't really know, but I have this sort of feeling that kind of the programming language theory people, which are sort of all the old Haskell people, are sort of migrating to Agda. So I know Phil Wadler is deeply into it. Thierry Coquin, who invented Coq, the big proof assistant, he's moved over. And in fact, the name Agda is a very bizarre play on him and his wife, who was the person who wrote the first Agda compiler. The big thing there is generally when we talk about types, you've got terms on one side, you have types on the other, and basically types are about talking about terms, and terms are completely unrelated. What you get with dependent types is the whole thing gets mixed, and that's what gives you. It's what gives you a huge amount of power. It lets you do the proof assistant as well as being able to write programs. And I'll actually walk through some of the first Agda code I wrote to show how that all fits together. So basically the idea was, if we say, okay, we can take these physical processes and express them using, I'll get to them, monoids and categories, we can do that in Agda, and we can actually prove that we have those things, and then we can write code to talk to that. So just a lot of math terminology will come flying out of my mouth, not all of which I will define given the time we've got, but if anybody wants to see, so just so you know what the terms are that I'm talking about. So this is the first bit of Agda code, and basically going to say, in a process, you've got a bunch of resources. You have resources coming in, you have resources going out, you may have resources that you reuse. So we can create a type of resource, and essentially what I'm saying, a resource is, it has a name, what kind of thing it is, and then there's some amount, which here I'm saying is just a rational, some rational number, and we have infinity at the bottom, so we have kind of a lattice. We can get to a lattice with infinity at the top, and you can just create lists of those. But the interesting thing here is, in the list of resources, when sort of you have a step in a recipe, it doesn't matter what order the resources are in, you just have a bunch of stuff, you've got the things you need for that step. So the order is not important, which means that we can sort these things, and if they're sorted, we can combine them in either way, and essentially what I've got, you see on the bottom, I've got butter and egg whites, and I unify that with a list that has egg whites and meringue, and essentially I end up with a list with butter, egg whites, and meringue, and I just sum up the egg whites so that we basically get everything together. Suddenly I'm much louder. All right, so I said I want to sort the list. And sorting is an interesting thing. So what sorted is a predicate. So basically I've got something and I can apply the predicate sorted to say that this thing is sorted. How do I know it's sorted? Well, it's a list which has been linked using some operator that is here written as less than. And what is linked? I'm going to walk away from the thing here so I can show you. So linked, I'm not going to. So linked, I've got three constructors. I've got an empty list, a list that has one object because there's not much to sort, or I want to add something. Sure. Or, until I'm not used to this. Or I have an existing list that has something on the top and I want to add something onto it, and I have to make sure that if I add that, it's in the relation that I've, in my less than or equals that I have up there. So basically, I can create a list in one of those three ways. Well, what is that less than or equal? And if you click around in the HTML generated from the standard library, you'll see that it's the less than or equals that from total order. And essentially, what that says is, something is a total order, I have to have some type of thing that I'm comparing, and then I need a way of comparing them for equality, and I need a way of ordering them. And then I have to prove that these things happen to be a total order. So what I did was I created two relations. One is for equivalence, one is for ordering, and then, as I'll show you in a second, I went and proved that these things I've created are in fact a total order. And once I've done that, I can take my total order, pass it into the sorting module, and I get out something I'm calling res sorted. Now, what I can do down here, it says d-resource is a type that's what's called the dependent pair type. So essentially what that says is I have a thing, calling m, which is of type list resource, and it's sorted. And then the last thing down there is, if I'm having lists of these things and I want to be able to use union, I need to be able to have something that represents an empty list, because that's kind of the identity that we're going to get to. Now, in order to prove that something is a total order, so first I have to define my a less than relation, equivalence relation, and Agda, I think it's even worse than Haskell in giving you the ability to define new operators like crazy. In fact, as somebody pointed out, if then else is a three-way operator in Agda. It's not defined in the language. If you say if, then you provide something then, you provide something else, and provide something. That's an operator in the language that takes three arguments that get interspersed. I'm not big on that kind of thing, but it's there. So I've defined these two things, and the constructors for less than and the constructors for equals are those things under there. And essentially, what it says is, what I did is, after spending a long time trying to figure out how Agda does this thing, I just said, well, I'm going to figure out how to a string display of these things, and I'm just going to compare strings. And if the string, string is already a total order, so I'm saying I can get a string out of these things. I use string compare, and that gives me my total order. So what I've said there is, I have there's the type, P is less than Q in this order, if I can give you proof that the display of P is less than or equal as a string than the display of Q. And if I can do that, then I have that P is less than or equal to Q in my sorting type. And then, so I've got that, and then I've also have a constructor for equivalent, which basically is the same thing. And so, okay, I have those two. And now the rest of these are proofs that, that the P is equal to P, which again I steal from string, because string already has a definition of reflexive. Then I've got, so that's equivalence. I've got if symmetry, or that if anti-symmetry, I've got if P is equivalent to Q, then Q is equivalent to P, and so on down the line. The last two were really weird, because basically what happens is the Agda compiler will figure out the arguments that you don't use. So anything in curly braces are arguments that the compiler is supposed to figure out for you. So I really can't explain to you exactly how it works, but basically what's going on in there is you give it partial values, and the compiler will go and figure out the ones you need, and your proof all works. So it's really interesting, because P less than or equal RQ is actually a type, and you can use that in this system. So if I give you two things, and you get that they are of that type, if that relationship holds. So since you need to prove things, I can't just get a list, sort it, and say, oh, this is a sorted list. I have to actually compose the list in such a way that the compiler can assure itself that everything is sorted as you build the list up. And I don't have the entire code here, but essentially, I start off with, well, empty list, that's empty. A list with one object on it, that's fine. So I've got the constructors for linked. And then finally, well, if I've got I ended up with two elements onto an empty list and then two elements on a non-empty list. But in the fourth case down, basically what I've got is I'm saying, okay, take the display values of x of the two the two things, and then go and figure out if they are of the desired type, or that it's a predicate. And if they are, well, I'll insert them one way, and if they're not, then I'll insert it the other way. And then finally, do basically the same thing with a list of 3. It's a little bit more complicated, and there's plenty of code that I haven't put in here. But when you do it this way, you build the list up from the end back, and it's provably correct. Really what it is bubble sort. And if I handed an already sorted list, it's an O of n operation rather than n squared. So I sort them, and then I hand them to this. Now, it turns out, where did I get it here? All the way over here. So I said the order of resources is unimportant. I can combine them into lists. I can determine that lists are equal, and I can unify lists either way, and I'll get the same thing. Which means that I have a commutative monoid. What is a monoid? And this is, again, is the definition of monoid in Agda. What is a monoid? Well, it has you've got those two things at the top defining this little dot operator and an equals operator that's local to commutative monoid, when one uses it places, one can fool around with what the naming is. So I have those two things. So what is a monoid? Well, I've got some type, and I've got the ability to tell that two things in the type are equal, which is, again, related to being a predicate. And then I can operate on those. And it says op2, and op2 basically says I'm going to operate on those, and that operator, I've got things, two operators, and it'll give me back a thing of that type. And then I've defined an identity, which is the empty list that I had before. And then, I'm not going through it, but I need to prove that it's commutative. And I mean, this is sort of the way the whole Agda standard library and the category theory library built is, you have this thing, you say these are the pieces of it, and then you have to go somewhere else and prove all the shit that you need to, you have to go somewhere else and prove all the things that you need to prove to make sure that it's that. So is commutative monoid, basically you're going to need to prove that the operator and the identity form a monoid, and you're going to have to prove that they're commutative. And what is commutative? Well, you're going to have to prove that whatever your operator is on that set, whichever way you go, you get the same results within the type. So that gives me a way of, I can now say I've got this monoid that has any list of resources that goes into my recipe is part of that monoid. So in a sense, I've got all of the inputs to any recipe that you wanted to do, assuming I have all of the different ingredient types included there. So I want to be able to then, well, I want to be able to put something in the oven and get it baked and do all the various operations. So what I do for that is I have a bunch of reduction rules where it's essentially this one says, well, if I have some pie pans and some weights and some parchment and some basic dough, I can fill up a bunch of tins with that. So I've got a pie pan. A filled tin is a different resource type, and it's an intermediate in the whole process. So you got that. And the other thing that I didn't tell you that I'll add is, so if you see between filled tins and baked crust, I've got this cycle around weights. Basically, I'm going to reuse the weights. And in order to reuse the weights, I need to be able to essentially to have positive weights and negative weights. Essentially, I'm saying I'm borrowing the weights, and I'm going to return the weights. And the easiest way to do that is I can just give a polarity to each of those, and the way that, if I union two things of the same type that have opposite polarities, I end up with the difference and whatever the sign is of the greater one. And of course, if anything ends up, if they're equal, it ends up to 0, and now I'm back to identity. So that reduces to identity. So just add those on, and everything has a polarity, and that's how you do the addition. All right. So with enough of these, I basically have a bag describing all the bits and pieces of any potential recipe of things that I can describe what you can do with things and and sort of what resources I have. I've got the bits and pieces of every possible recipe, but I don't have any recipe. So what's a recipe? A recipe is a fixed set of those that link together. And that's where we get to categories. So first thing, I assume probably most of the people in here, since category theory caught their attention, what the basic idea of a category is. You've got a bunch of objects, and you've got a bunch of edges, and you have identity morphisms, which I left out of here, and you have a composition operator, and then you add more things to it, and you've got all the various different categories that you've heard of. One kind of category is a symmetric monoidal category, and basically there you have this bifunctor that says if I have two objects of type C, I can get another object of type C, and I have an identity, and I have a morphism from the identity to every object in the category, and there are a few other things. But essentially, you can take pretty much any monoid, and we have a monoid, and get a monoidal category. So, and there, the objects are all the lists become objects. And any reductions, all the reductions are morphisms within the category. So now we get to the interesting thing, and this is what I learned about category theory when I entered this process, and I'm going to guess most of you probably don't know about it. So the big thing in category theory are what are called enriched categories. And in enriched categories, you have a class C of objects, like we had before, but between every object, rather than having a bunch of morphisms, which you can put together as a set if it's a small category and call that an object, between every one of those you have an object called the Ham object. And the Ham object is an object in a different category, which happens to be a monoidal category. Not necessarily symmetric, but we're symmetric. So you have an object from some other category. And for every pair, you have a little operator that So what have you got here? So you have in the monoid, you have an arrow from identity to the id loops of your category here. You see, that's pretty straightforward. And you have a composition arrow that says from between any two objects in my class C of objects, I have an edge to some other object which is in the monoid. And in this case, that lets me take all of the empty edges I haven't defined and just identify those with the identity morphism. So for that, I can create a diagram in some category that has sets of ingredients on the edges. And then I can put, in this case, I want to put reduction operations at the nodes. And that describes the recipe. And you can just sort of move stuff along, and then you've got all the bits and pieces of the recipe. How am I doing for time? I got 5 minutes. OK, that's why I said I was going to talk fast, because I had a fair amount to get to. So there's two other bits and pieces. One is I've got that diagram, which gives me a category about stuff. But then I want to be able to do things. I want to be able to analyze. I want to be able to look at it in different ways. And I can use functors to do that. In particular, I can use a profunctor. And a profunctor is an interesting thing. It's a functor from a cross product of two categories into set. And basically what that says is and generally the first one is in the opposite category, which means that basically I can take any object with inputs and outputs, and since I'm dealing in the op category in one of those, I've got the cross product of everything, but I've got a bunch of cases where I have edges that now have the same object as target, and from there I can go, okay, I've got this thing. For example, how long does it take somebody to fill out those tins? I've got a bunch of dough coming in, dough and stuff coming in. In the end of it, I come out with 4 tins. How long does it take to do that? And from there, I can go from this underlying thing to a list of times, and then interesting last piece. And I can map to all sorts of things. So there's like lots of questions I can ask about stuff in the underlying recipe that I can answer by basically going into another category where I can ask different questions. So the last thing is that I can, so now I've got a new category. I've got values for the nodes, but I want to ask about something about the entire graph. It turns out that a lot of these things turn out to be semi-rings. And at the end of this, anybody who's been listening to the APL talks is going to go, yeah, we knew that. Why did you go all the way around to get to the same place? But all of these you can define a lot of these as semi-rings, and a semi-ring is just something, you've got a set. The set, you've got something in this set you can call 1, something in this set you can call 0, and you've got one function that's, takes two elements from that set and gives you back another one of them that behaves like plus, and another behaves like times. And all of a sudden, you can do array manipulation on these things, which is why the APL people are looking and going, what the hell? Why? So that means that I can map things into various different ways and in various different other categories for analysis, and then use matrix, just Floyd-Warshall's algorithm in various ways to get values for what is happening in this recipe from that perspective. So, and here's an example of that. So I can look at, I can take a set of values of stuff coming into or leaving a bunch of nodes. I can multiply that by the values of the morphisms. And if I use multiplication as intersection and addition as union, I can basically walk my way through all of the steps of the recipe. So one of the interesting things about using math, if you use math as a framework, so you get a huge amount of power. So here it's like, well, one could create, I've given you a definition of resources. One can create any different sets of resources, and everything else I've said will apply. So I just used a simple recipe, but anything else where you have a process that involves taking inputs and transforming them to outputs fits into this framework. And it is true that there is work to be done in doing the proofs, but after that, everything just applies. So if you can express your problem as a monoid in a semi-ring, you get everything else I've done for free, which is why all the APLers are looking, or should be looking at me going, but we knew that. That's the value of coming to a place. You get to like add on a final line that you never would have thought of. Anyway, we have 1 minute for questions. Told you I'd talk fast. Nope? Anybody? All right.
Thank you.
Thank you.